Swayam Prabha. Digital India. Educated India.
Hydrogen ions in plasma remain within a very narrow range around 40 nanomoles per liter in spite of addition of acid to venous blood. Constant addition of acid to venous blood resulting from metabolism of cells. In the previous session, we considered how the pH of arterial blood is kept at 7.4. We started with carbon dioxide concentration of 1.2 millimolar and showed Sajal's experiment where addition of this much carbon dioxide to plain water resulted in a pH around 5. And then we said pH of plasma is not so low but remains 7.4 because of an excess of bicarbonate in blood. We then came to a point where we realized that it is bicarbonate in arterial blood that is necessary for some reason. The kidneys keep putting out bicarbonate into blood so as to maintain their concentration so high for a purpose, and that might result in alkalinization of blood because we saw the reaction where bicarbonate ions can generate hydroxyl ions and that will increase the pH. Just like Sajal's experiment, Natarajan, a senior technician with us, did this experiment. He added 24 millimoles per liter bicarbonate to plain water and saw that the pH was 8.6. That does not happen in blood either. Therefore, the increase in pH due to addition of bicarbonate is kept at bay because of the presence of carbon dioxide in arterial blood. The lungs titrate the amount of carbon dioxide that need to enter arterial blood so as to maintain the ratio of carbon dioxide to bicarbonate at 20, and therefore you will get a pH 7.4. So carbon dioxide and bicarbonate in the right amounts balance each other so as to maintain pH of arterial plasma at 7.4. In this session, we will take up the question, what happens with addition of acids to blood as it courses through tissues? The major output from tissues into venous blood is carbon dioxide. In this session, we will consider issues that arise due to addition of carbon dioxide to venous blood, and in the next session, we will consider what happens due to addition of fixed acids. How much of carbon dioxide is added to venous blood? We have considered this in the very first lecture. Carbon dioxide output per day is about 20 moles or 20,000 millimoles per day. The cardiac output is 5 liters per minute, and in a day there are 16 to 24 minutes, and therefore the blood flow through tissues is 7,200 liters per day. We can then work out the carbon dioxide output per liter of venous blood that courses through tissues as this value divided by the blood flow per day, and that gives us about 3 millimoles per day, 3 millimoles per liter. When 3 millimoles per liter of carbon dioxide is added, what happens to the carbon dioxide concentration of venous blood? In arterial blood, it was 1.2 millimoles per liter, and that amount is allowed to escape the lungs and come into arterial blood. In fact, the respiratory system, the respiratory center in the brain regulates ventilation so as to maintain a carbon dioxide concentration in arterial blood that would exactly balance whatever bicarbonate concentration there is so as to maintain the ratio of bicarbonate to carbon dioxide at 20. In the normal circumstances, we have 1.2 millimoles per liter carbon dioxide in arterial blood, and we have 3 millimoles per liter carbon dioxide being added into venous blood. What happens to the concentration of carbon dioxide in venous blood? Does it go up to 4.2? Is there just addition of that value? Not really. We find that if we take a sample of mixed venous blood near the right heart, let us say from the central vein, then we would get a carbon dioxide concentration of 1.35 millimoles per liter only. Therefore, all the 3 millimoles per liter that comes in must be processed to give something else, and only a small amount of that remains dissolved as free carbon dioxide in addition to what is already coming from arterial blood. So, what happens to the bulk of the carbon dioxide that comes into venous blood? At this point, let me tell you that carbon dioxide concentrations are measured as partial pressures of carbon dioxide. Partial pressure of carbon dioxide in arterial blood is 40 millimeters mercury, and that in venous blood is 45 millimeters mercury. For every millimeter mercury partial pressure, 0.03 millimoles per liter will be dissolved in liquid, and therefore, for a PCO2 of 40 millimeters mercury, we get 40 into 0.03, 1.2 millimoles per liter carbon dioxide. The conversion factor is 0.03. What do we exactly mean by partial pressure of a gas in a liquid? That we will see at the end of this session. For now, we will treat carbon dioxide concentration as they are. But you must remember, if you've seen arterial blood gas reports already, what are called ABG reports, you would see that carbon dioxide concentrations are reported as PCO2. Well, while 3 millimoles per liter carbon dioxide comes into venous blood, only 0.15 millimoles per liter increase occurs in the concentration of carbon dioxide that is already there in the arterial blood. What happens to the rest of the carbon dioxide? We know that carbon dioxide moves into red blood cells and reacts with the water phase of the red blood cells of the cytoplasm to form carbonic acid. Red blood cells have the enzyme carbonic anhydrase and can accelerate the reaction where carbon dioxide gets hydrated. Carbonic acid will protonate to yield hydrogen ions and bicarbonate ions. If you remember, this reaction, this forward reaction was not allowed to happen in arterial plasma, or rather it did not happen in arterial plasma because of the excess of bicarbonate in arterial blood, However, this forward reaction is accelerated within red blood cells because red blood cells have the enzyme carbonic anhydrase, which can facilitate this reaction. The question now is, what happens to the pH of red blood cells? Would the protons here decrease the pH of red blood cells? Will it cause acidification? That does not happen because hemoglobin in the red blood cells can bind free protons, and therefore the pH of red blood cells does not decrease. It is only free protons that contribute to acidity or pH. It is not enough for hydrogen ions or free protons alone to be removed from the system. Hemoglobin has bound the free protons and that's what we say, has buffered the acidity. It has not allowed pH to drop because it has bound the free protons. That alone is not enough. Unless we remove bicarbonate from the system, something like this would happen. Bicarbonate would build up and the reaction will not be able to proceed further. We want the reaction to go on so that all the carbon dioxide that comes out from the tissues is handled by the red blood cells so as to remove the acidity of carbon dioxide by allowing those protons to combine with hemoglobin. The system must see to it that bicarbonate is also removed from red blood cells so as to keep this forward reaction going on. How does bicarbonate get removed from red blood cells? You've learnt this at school. All of you know about the famous hamburger's chloride shift, there is this protein called anion exchanger on the red blood cell membrane. It is called the band 3 protein because in an electrophoretic gel, this protein would come as the third band, a very large band. The anion exchanger will exchange these two anions. As bicarbonate ion concentration within the cell builds up, it would be moved to plasma. So as to maintain electroneutrality within the cell, chloride ions will be taken in. Now, remember, these bicarbonate ions have come in from red blood cells, and this is going to be over and above the bicarbonate ions that have moved into venous blood from arterial blood. Already there was a bicarbonate concentration of 24 millimoles per liter, and now the erythrocytes are adding more bicarbonate. How much more bicarbonate? If we had 3 millimoles per liter carbon dioxide coming in, and if this reaction were to proceed continuously, then we will have about 3 millimoles per liter bicarbonate being added to venous blood. Bicarbonate concentration has now gone up to 27 millimoles per liter, and chloride concentration in venous blood would have dropped by about 3 millimoles per liter. Before we consider what happens to pH because of this excess of bicarbonate ions in venous blood, we will see what happens when erythrocytes reach the pulmonary circulation. As red blood cells flow through pulmonary capillaries, oxygen has entered the capillaries and has moved into the red blood cells. Oxygen binds to hemoglobin, and oxyhemoglobin, you would have read that it is a stronger acid, which means it is not going to keep the hydrogen ions bound to it, but will release the free hydrogen ions. Oxygen will literally knock off the free hydrogen ions from hemoglobin. Now, this will lead to a decrease in pH within the red blood cells, and let us say that the drop in pH in red blood cells will reverse the anion exchanger. It will now take in bicarbonate ions and release the chloride ions that it had taken up in the systemic venous blood. Now, because the products of this reaction are building up, hydrogen ions and bicarbonate ions will combine to form carbonic acid. The reverse reaction will proceed in the pulmonary capillaries. Carbon dioxide is liberated and is exhaled. Therefore, all the 3 millimoles per liter of carbon dioxide that comes into venous blood is eliminated as blood courses through pulmonary capillaries. 3 millimoles per liter of carbon dioxide is removed from pulmonary circulation and exhaled. The question to resolve now is, while we saw that though so much of carbon dioxide came into venous blood, it did not exist as carbon dioxide per se. Only a small amount of carbon dioxide remained in the dissolved form. The rest of it moved into red blood cells and was actually traveling as bicarbonate in plasma. And then we saw how carbon dioxide is evolved in the lungs. So, in arterial plasma, pH was 7.4 because the ratio of carbon dioxide and bicarbonate was 20 as per the Henderson-Hasselbalch equation. These two substances will reach the venous blood as well. However, in venous blood, because of the reactions within red blood cells, some more bicarbonate was added. We could call this as the renal component of the bicarbonate compartment, and this the erythrocyte component of the bicarbonate compartment. So, this small excess of 3 millimoles per liter which came in from red blood cells could disturb the pH, albeit in a very small way. Does that happen at all? Not really, because a very small amount of carbon dioxide, just 0.15 millimoles per liter, is allowed to remain dissolved as carbon dioxide per se, so that the venous carbon dioxide concentration is 1.2 plus 0.15, that is 1.35 millimolar, and the ratio of bicarbonate to carbon dioxide still remains 20 even in venous plasma. This was a eureka moment for me when I understood that there's something that dictates how much of carbon dioxide can remain dissolved in venous plasma, so that the ratio of bicarbonate to carbon dioxide in venous plasma also remains around 20. I still have not been able to figure out what decides how much carbon dioxide that comes in from tissues can remain in the dissolved form and how much of it has to become bicarbonate so as not to disturb the pH of blood. So, in spite of addition of carbon dioxide to venous blood, that carbon dioxide distributes itself as bicarbonate and free carbon dioxide in venous plasma so as to keep the plasma pH at 7.4 even there. Since there seems to be a system that regulates the amount of carbon dioxide that has to dissolve in venous blood, any real change in carbon dioxide concentration in blood will occur only if the lungs fail to titrate how much carbon dioxide should escape into arterial blood. Addition of carbon dioxide by the tissues into venous blood does not change the free dissolved carbon dioxide to such an extent as to cause acidification of blood, because whatever is added can be handled adequately within red blood cells and hemoglobin can capture all the protons that are formed. Therefore, addition of carbon dioxide into blood per se will not alter the pH of blood. In that sense, hemoglobin is the most important buffer system in our body, which handles much of the acid output due to tissues. We have seen earlier that the predominant acid output from tissues is carbon dioxide, and there is enough hemoglobin even in an anemic person to handle all the protons that may be released due to addition of carbon dioxide into venous blood. Hemoglobin is by far the most important buffer system in our body, therefore. It binds protons where they are formed, and when the red blood cells reach an area where the protons can be eliminated, hemoglobin will give up those protons to react with bicarbonate, form carbon dioxide and eliminate the acidity. In our clinical considerations, we will not even talk about hemoglobin because it is such an efficient system that there is no pathology arising due to hemoglobin's ability to bind free protons. And therefore, we sometimes do not appreciate the importance of hemoglobin as the most important buffer system in our body. To summarize, pH of blood is 7.4 in arterial blood because of the ratio of bicarbonate to carbon dioxide concentrations. It is at 20. When blood courses through tissues, 3 millimoles per liter carbon dioxide is added to blood, but that does not affect the pH again because most of that carbon dioxide moves into red blood cells. The protons formed as a result are buffered by hemoglobin. The carbon dioxide is captured as bicarbonate and travels as bicarbonate in plasma. But even that slight excess bicarbonate from the erythrocytes does not affect the pH of venous blood because there seems to be some mechanism by which the right amount of carbon dioxide is allowed to remain dissolved in the free state in venous blood so as to maintain the ratio of bicarbonate to carbon dioxide at 20 even in venous blood. And when blood reaches the lungs, the reverse reaction occurs because bicarbonate moves into red blood cells. Hemoglobin releases the hydrogen ions once oxygen combines with it. The reverse reaction occurs and carbon dioxide is eliminated. Now we will see how carbon dioxide concentrations are measured in blood. The arterial carbon dioxide concentration is 1.2 and the venous concentration is 1.35. But blood gas reports that you get from labs will not give you these values. They will only give you partial pressure of carbon dioxide in arterial blood, PaCO2 at 40 millimeters mercury and PvCO2 or venous PCO2 at 45 millimeters mercury. We have seen earlier that the conversion factor is 0.03. 40 into 0.03 will give us 1.2 and 45 into 0.03 will give us 1.35. What do we mean by partial pressures of gases in liquids? This is a question that some students have asked. Hydrostatic pressure of blood on the lateral walls of arteries is 120 millimeter mercury at the peak of systole, and at the end of diastole it is about 80 millimeters mercury. 120, 80 is what we report blood pressure as. Now, how do these partial pressures, let us take arterial blood. What do we mean when we say partial pressure of carbon dioxide is 40, partial pressure of oxygen in blood is 100 millimeters mercury? What do we mean by such statements? How do these partial pressure fit in to the hydrostatic pressure of blood itself, or how do they matter for the blood pressure? What is essential to understand is that gases and liquids do not exert any extra pressure on the walls of the artery. The hydrostatic pressure that is felt by the walls of the artery is entirely due to the liquid blood. What do these terms refer to then? Partial pressures of gases in blood. Gases which are dissolved in blood do not exert any pressure, but why do we speak about partial pressures? Remember, earlier we saw an experiment that Sajal did where he left some water in the CO2 incubator. The incubator had 5% carbon dioxide in it. That is, the mixture had 5% carbon dioxide. If the air mixture, any air mixture will be at the atmospheric pressure, 760 millimeters mercury would be the total pressure of the air mixture. If there was 5% carbon dioxide, the partial pressure due to carbon dioxide would be 5% of 760, which is 40 millimeters mercury. And in that environment, so much carbon dioxide would dissolve in plasma. That is the carbon dioxide equilibrium. For every millimeter mercury carbon dioxide, 0.03 millimoles per liter will be the dissolved carbon dioxide. When we estimate carbon dioxide concentrations in blood, we do the reverse. We take a sample of blood into a test tube. This is not exactly how it is done, but the principle is this, and the tube will be capped. Carbon dioxide will now allowed to evolve out of the blood sample into a very small space above the sample. And then after equilibration, the partial pressure of carbon dioxide in this atmosphere is estimated. How actually it is estimated is beyond the scope of this class, and you could refer to this publication to see how exactly PCO2 is estimated. So, when the PCO2 of the atmosphere above the sample of blood is 40 millimeters mercury, then it is inferred that the carbon dioxide concentration in that sample of blood would be that into 0.03. That is what we mean by partial pressures of gases in liquids. The concentration of the gases, either carbon dioxide or oxygen, in that sample of blood or liquid is such that when it is allowed to evolve into a small space and equilibrate, that atmosphere above the sample of blood will develop those partial pressures. Therefore, partial pressures of gases are real in atmospheric air or in any atmosphere of gases, and those partial pressures will not exert pressures within the liquid, but they will yield corresponding concentrations of the gases in the liquid. I hope I have conveyed my understanding of what we mean by partial pressures of gases and liquids. In the next session, we will consider issues due to addition of fixed acids into blood. Thank you for watching.